Ever wondered how the arrangement of atoms in a crystal determines its properties? Welcome to the fascinating world of crystal structures. These structures play a pivotal role in material science, helping us understand the unique characteristics of various substances. At the heart of these structures are crystal lattices, which are essentially repeating arrangements of atoms. These lattices form the blueprint of a crystal, mapping out its atomic layout. So, the secret to a crystal's properties lies in its lattice structure. But what's the smallest unit of these lattices? Ever heard about the unit cell? Well, let's dive in. A unit cell is the smallest repeating unit in a crystal lattice. It's like a tiny, three-dimensional blueprint of the entire crystal structure. The way the atoms are arranged in a unit cell, whether tightly packed or loosely scattered, directly influences the physical properties of the crystal. So, the hardness, density, even color of a crystal can all be traced back to its unit cell. In essence, a crystal's properties are a reflection of its unit cell. Did you know there are different types of lattices, each with its unique atomic arrangement? Let's dive into the world of SC, FCC, and BCC lattices. First, we have the simple cubic, or SC lattice. As the name suggests, it's the most straightforward of the lot. The atoms are arranged in a basic cube shape with one atom at each corner. Next up is the face-centered cubic, or FCC lattice. Picture a simple cubic lattice, but with an extra atom smack in the middle of each face of the cube. This results in a higher atomic density and better packing efficiency. Finally, we come to the body-centered cubic, or BCC lattice. Similar to the FCC, the BCC has atoms at each corner of the cube. But here's the twist. It also has an extra atom in the center of the cube, effectively creating a higher atomic arrangement. These are the three main types of lattices. Each has a unique way of arranging atoms. Now, let's dive deeper into the unit cells associated with each lattice type. We'll start with the simple cubic, or SC lattice. In an SC lattice, the unit cell is a simple cube, with atoms positioned at each of the 8 corners. This straightforward arrangement results in materials that are relatively easy to analyze and understand. Next, let's move on to the face-centered cubic, or FCC lattice. Here, the unit cell is also a cube, but with an extra atom positioned at the center of each face. This configuration leads to a higher packing efficiency, and thus, materials with FCC lattice structures exhibit excellent balance between strength and ductility. Finally, we have the body-centered cubic, or BCC lattice. Unlike the FCC, the BCC unit cell has an extra atom positioned right at the center of the cube. This unique arrangement results in materials that are denser and stronger, yet more brittle compared to their FCC counterparts. As we've seen, the arrangement of atoms within the unit cell plays a crucial role in determining the properties of the material. From the simple SC to the more complex FCC and BCC, each lattice type offers a unique set of properties, making them suitable for different applications. From the metals that form the backbone of our infrastructure to the semiconductors that power our devices, these structures are fundamental to our world. These unique unit cells define the properties of their respective materials. Wondering how these lattices compare with each other? Let's dive in. Simple cubic lattices, though straightforward, have the lowest packing efficiency and stability. On the flip side, face-centered cubic lattices with atoms nestled in their faces boast a higher packing efficiency and stability. Then we have the body-centered cubic lattices, striking a balance between the two with an atom at its center. So, while they all share the basic concept of a lattice, their atomic arrangements and densities vary, giving each a unique set of properties. Despite their similarities, these lattices have quite distinct characteristics. So, we've covered quite a bit about crystal lattices and unit cells. We delved into the world of SC, FCC, and BCC lattices, explored the unique features of their unit cells, and compared their packing efficiency and stability. Remember, these structures aren't just theoretical constructs, they're the building blocks of the materials that shape our world. This is just the tip of the iceberg, and I encourage you to dig deeper. Stay curious and keep exploring. There's so much more to learn about the fascinating world of crystals.